Hey everyone, my name is Christian Ampalo, one of the presenter of Group and today we will be presenting all about flash separation of acetone-methanol with my fellow groupmates Banishin, Inurin Hushna, and Nasrul Daim. But before we proceed with the objective of this project, let me introduce what this project is all about. Flash distillation is a separation process of liquid mixture that has different volatility components. It is a type of distillation that involves the sudden vaporization of liquid with lower boiling points caused by a sudden pressure drop, while the higher boiling point liquids remain in liquid form. The system is called flash distillation because the vaporization happens rapidly as the fluid enters the drum. Flash distillation is viable for separating the acetone-methanol mixture because the components have different volatilities. Acetone boils at 56.06 degrees Celsius, while methanol boils at 64.7 degrees Celsius. Because acetone is more volatile, it vaporizes more readily than methanol under the appropriate temperature and pressure condition. As a result, the vapor phase becomes richer in acetone while the liquid phase becomes richer in methanol. Flash distillation is an excellent approach for this mixture because it is simple, has low operating costs, and enables rapid phase separation, which is why it is widely used in chemical and petroleum industries. The objective of this project is to design a flash distillation process for separating an acetone-methanol mixture. Next is to identify the equilibrium liquid and vapor composition, and the other one is to identify the amount of each phase produced under specified operating conditions.
So next will be our process condition. Our specific task is to separate a binary mixture consisting of component 1, which is the acetone, and the component 2, methanol. So for this case study, we evaluated a feed stream with a total of 1 mole of mixture. The feed composition is set at a mole fraction of 0.6 for the acetone, which is listed as Z1, and 0.4 for the methanol, which will be listed as Z2. The system is operated at a steady state temperature of 60 degrees Celsius and an atmospheric pressure of 1 atm, which is also equivalent to 101.325 kilopascal. So next will be the process diagram. As shown in our process scheme, the initial feed enters the single stage flash drum where it undergoes a sudden pressure drop causing rapid vaporization. So to perform our calculations effectively, we establish 4 key engineering assumptions. The first will be the ideal behavior, which the mixture will act as an ideal solution where Rock's law is fully valid. The second will be the steady state operations. The flow rates, temperature, pressure, and the stream compositions will remain constant over time. The third one will be the phase equilibrium, which the exit vapor and liquid phases achieve a perfect thermodynamic equilibrium, meaning that there is no further net mass transfer takes place. And the fourth assumption will be the uniform pressure, where the inlet and exit pressures are uniformly maintained at 101.325 kilopascal. So next will be the flash calculation. Moving into our thermodynamic calculations, our first step is to determine the saturation pressure for both components and our operating temperature of 60 degrees Celsius. We utilize the empirical Antoine equation, which we have listed in our slide, and by pulling the component constant from literature, which we listed in the table, and plugging in the T equals to 60 degrees Celsius, we get to calculate that the saturation pressure for the acetone will be 115.1557 kilopascal, while the saturation pressure for the methanol will be 83.9891 kilopascal. And next, for step 2, we need to determine the bubble point pressure by assuming the feed composition represents the liquid phase, which in this case, the Z1 will be equals to Xi. And by using the equation listed in the slide, we get to know that the bubble point pressure will be equals to 102.6891 kilopascal. While for step 3, we need to calculate the dew point pressure by treating our feed composition as the vapor phase, which in this case, Zi will be equals to Yi. And by using the equations listed, we get to know that the dew point pressure will be calculated as 100.2721 kilopascal. Well, next we are going to moving on to step 4, which step 4 is very important as we must confirm that a two-phase equilibrium region is actually exists at our operating pressure by comparing between the pressure of system, bubble point pressure, and also the dew point pressure. Because our system operating pressure falls squarely between the dew point and the bubble point pressures, we have verified that the mixture splits into a two-phase vapor liquid system. And for step 5, we need to evaluate the equilibrium distribution coefficients Ki for both species using the Rod's law, which is Ki equals to Pi saturated over total pressure. So for acetone, we get to know that the K1 will be equals to 1.1365, and for methanol, we get to know that the K2 will be equals to 0.8289. So, moving on to step 6, it requires us to find the molar fraction of the feed that vaporized, denoted as V. We manipulate the Rutherford-Rice equilibrium criteria, which is the first equation that listed in our slide, to establish an algebra arrangement optimized for the sequential spreadsheet iteration, which the final equation will be listed at the below of our. Using the Microsoft Excel to loop this equation until our error smaller enough, the vapor fraction converged to exactly V equals to 0.5763. With our vapor fraction solved, we compute the exact compositions and remaining liquid mass in steps 7 through 9. The vapor composition Yi are extracted from the equation that listed in the step 7 in the slide, while finally, the acetone in vapor will be 0.6322 and the methanol in the vapor will be 0.3678. By using the phase equilibrium Xi equals to Yi over Ki, we get to find our liquid phase compositions, which the acetone in liquid will be 0.5562 and the methanol in the liquid to be 0.4438. And lastly, by applying a total molar material balance, L will be equals to F minus V, and in this case, the F will be equals to 1. The total amount of the liquid remaining will be 0.4237 mole. So, to wrap up our calculation, let us look at our final process summary data, which we listed in our summary table. So, the mole of the liquid will be 0.4237, and the mole of the vapor will be 0.5763, and the total mole fraction will be 1. While for the liquid phase mole fraction, the acetone will be 0.5562, and the methanol will be 0.4438, while the total mole fraction will be equals to 1 as well. And the vapor phase mole fractions for acetone will be 0.6322 and the methanol to be 0.3678, and the total mole fraction will be 1.
And next, for the suggestion part, to get the better flash separation design, we should optimize the physical vessel for the feed mixture. Other than that, the bottom liquid section of the vessel must be sized to store the methanol liquid with an adequate hold-up time. And the third one, the internal diameter of the flush drum should be calculated by establish the maximum allowable vapor velocity. And the last one, we can allocate specific spatial zones inside the vessel, such as a top section for vapor de-entertainment, a middle section for the feed inlet nozzle, and a bottom section for liquid inventory.
So the data presented summarized that the successful design of flash separation unit for an acetone and methanol, which is binary mixture. This mixture operating at 60 degrees Celsius and 101.325 kPa with a feed composition of Z1 equal to 0.6 and Z2 equal to 0.4. The key outcomes are as follows, which is phase distribution. The process resulted in a vapor fraction of 0.5763 mole per mole of feed and a liquid fraction of 0.4237 mole per mole feed. Next, for the composition profile, the vapor phase is enriched with acetone, achieving a composition of Y1 equal to 0.6322 and Y2 0.3678. The remaining liquid phase has a composition of S1 0.5562 and S2 equal to 0.4438. In conclusion, single stage flash drum is a feasible method for the partial separation of this binary mixture or enriching acetone in a vapor phase. While the ideal solution assumption utilized here is suitable for preliminary design, it is recommended that non-ideal activity coefficient models be applied for more rigorous industrial scale applications.